In this lesson, we're going to talk about finite element analysis and how you perform an FEA study in Solidworks and kind of generally some things to look out for and how it functions. So if you haven't done so already, go back and read the Lab 11 reading on stress and FEA, or else a lot of this probably won't make too much sense. So setting up FEA to run correctly is usually pretty difficult. And it's really common to get lots of error messages and to get a little bit frustrated getting your model set up correctly. And that's totally normal. So getting an FEA simulation set up correctly can sometimes even be impossible. It's ways to design things in the computer that are physically not possible. And what happens is the solver just gets confused. So from the reading in FEA, you're looking at breaking a component up into lots of little discrete areas and looking at how that area interacts with the ones around it. So in really ultra simplified explanation, FEA is just a bunch of matrix math. It's just looking at how those elements contact and stretch the ones around it. So in that regard, the software doesn't know which direction is up or down, or if there's gravity or not, or how much gravity until you tell it that it's there. And one of the important things when you're performing a static study is to make sure that your part is constrained in static equilibrium. Something in the model has to be constrained, fixed in space, or the model would go flying off in one direction when you apply a force to it. So everything has to get reacted somewhere. And let's take a look at what that looks like in the context of the tutorial that you're going to be working on here. So let me open this up. So in this tutorial, you're going to be performing a simple load analysis on this bracket. So I've already got mine open, but if you don't have simulation running already, you're going to need to go up to Tools at the top and then Add-ins and make sure that simulation is checked and that it's running in the background. If it's running, you should have a tab up here at the top outside of just designing your features for simulation. So you go to simulation and create a new study, and the study appears down here at the bottom next to the motion study tab that we already looked at. So the simulation tab opens, same as in motion study, another feature tree of things that you need to select. So as you go through the tutorial and as you start working on structural analysis for parts that you're working on for your project, when you open this up, you're going to start at the top and work your way down through all of these options. And you don't necessarily fill in all the options depending on what you're working on. Some of them only apply to like assemblies, for example. So the first thing that you do that we just covered is you're going to tell the program what material that this part is made of. So the tutorial has you select alloy steel. If you go to the next entry, it's called connections. So connections is what you would fill in if you're working with an assembly with multiple parts. And that's how you tell it how the parts interact with each other. So if you go to connect, if you have an assembly open, like with multiple parts, for example, this one, and I create a study, and I'm going to go to connections. So it's already filled in a connection for me. It's filled in that there's component contact between these two. So if you go to connections and look at contact set, I can tell it how my parts interact, whether they're allowed to pass through each other, if they're bonded together. That would be like if the parts are glued together, if there's a shrink fit around each other. So we'll get more involved with this when you have to work with assemblies, but that's what generally exists within the connections dialog. So the one after connections is called fixtures. So fixtures is how you tell the computer how your parts are constrained. And when you go to create one of these, the first one it's going to have you do is create a restraint that's fixed geometry. So when you go into fixtures, the menu gives you these couple different options, and the graphic shows you what that option means. And one thing I want you to be really cautious about when using the fixed geometry constraint is it's really easy to make your model, it's easy to make your simulation incorrect by misusing this one. So if you look at the graphic, of the bar moving around. What the fixed constraint means when you select a face is it means that it's almost as if you glue that face fixed in space, and it's not allowed to translate, and it's not allowed to distort or warp or anything like that. So you can imagine if you have components attached to each other, there's essentially never a real situation where the geometry and location of your part is completely fixed. Because remember, since everything's a spring and everything moves and deforms a little bit, you have to be careful how you use this one. And we'll take a look at that in this example when we put load in the bracket. So as we get into it in more detail, you'll experiment and play with those fixtures a little bit more. Then the next one is the loads. Loads appear on the model here as these red arrows. So the fixtures are green and the loads are red. And what we're going to do is we're going to attach this bracket using the bolt holes and then put load on one face. So when you go into loads and you create a load, there's all these different ways that the software can simulate different forces and loads being fed into your part, whether it's a twisting force or pressure, or it will do temperature simulations if you have the part go through a temperature transition to see how it expands and contracts and things like that. Then the next one, as you go through and setting up, is the mesh. So if you remember from the reading, the mesh is basically how many little elements you simulate your part is made up of. So I've created the mesh sort of in the middle of the menu here. So in the tutorial, it has you just select what the default mesh size is. So if you go create mesh, there's the slider at the top. There's more options beyond that, but this is a really convenient tool to speed up how quickly you can run simulations. So a lot of times you want to iterate your simulation really quickly. And like I said at the beginning, it's common to see a lot of errors. If you set the mesh really coarse, what it does is it makes fewer elements for the computer to have to solve all the interactions between those points. And what that means is it runs your simulation a lot faster. Well, the downside is, you might be able to guess, if you have a coarse mesh, it's a lot coarser resolution, and it's not as accurate where there's high stress around things like where your restraints and your forces are. So once you get your model running properly, sometimes it's advantageous to turn the mesh a lot finer, and you'll watch while it generates. Compared to what it took last time, it even takes longer to generate the mesh than it did last time. So now there's many, many, many more elements, and this means that my simulation is going to run a lot slower. So that's something that you can play with as we get into a little bit more detail there also. So I'm going to make this coarser again so that it doesn't take too long to run. And then I'm going to run this simulation. So the report that you're going to generate at the end of this is going to have you look at these 3 different result files that showed up at the bottom of the simulation tree. And the first one is stress. So there's stress, displacement, and strain. The stress plot is, like we talked about in the reading, it's the force being applied to a particular area in the part over some cross section. So it's force over area are the units for stress. And if you look at the right side of the screen, you see this legend for the color chart. So what the color chart means is that the higher up on the chart, the higher the stress. So the blue areas are low stress, they're safe. The high areas are red, and that's where the part's distorted. Excuse me, not distorted, that's where the highest stresses are. It can be a little confusing looking at the way this chart is laid out, because by default, the software puts everything in scientific notation and it makes the numbers look a little bit funny. So if you were going to look up in a chart of materials, the stress that a particular material will take will be listed in there, and you want to switch that over to the units that you're looking at. So this is how you look at how much stress is in your part. If you look at the next the next result, displacement. Displacement is just the distance the part moves. So you see that the layout of the colors on the part are different, but it animates in the same way. And an important thing to note is that the software is exaggerating how much this part moves on purpose to make it easy to visualize what you're looking at. So if, for example, if you right click on it and go to edit definition, these top three options give you a lot of ways that you can manipulate what this looks like. So if I go to edit definition, and then I look here at the deformed shape box, it's selected that it's automatically scaling how much this part moves. So right now it's set on my computer to about 12. If I set it to true scale and I watch the animation again, then based on the loads and the fixtures that I put in here, this is how much the part actually should move. And that can be useful if you're trying to figure out if something is going to bend so far it's going to touch another part or something like that. But for the sake of looking at where the most motion is, it's not as immediately obvious here as it is when it's really, really exaggerated. So it's usually a good idea to make sure that the display is set up. So I'm going to change it manually to a multiple of 30. So now it's really, really obvious where the motion is going to happen. And this is where I want you to look at why I said that those fixed constraints, that the fixed geometry constraint might be creating something unrealistic. So in this case, the fixed geometry constraint is applied to the inner diameter or the inner surface of these holes where probably bolts would go through to hold this bracket. So if you look at when the animation is running, if you zoom in these areas, you can see that those holes aren't warping at all, but the area right next to where the holes are is moving a lot. So what that tells you, you also can see on this back corner, for example, it's moving. This doesn't look like a realistic way that you would expect this to move. Because when you put a bolt through a hole, it's the top of the head of the bolt and the nut that are actually holding some surface around the surface of the hole rather than on the inside diameter of it. So if this was put together with screws or something, this is not a correct representation of what this would be doing in real life. That was what I was saying. We'll have to work towards, you have to work towards practicing constraining your parts as they would be in your real assembly. And then the last result file that it shows you is strain. So strain is just the percentage of change of length of some area of the part. So this is showing you how much any individual element within that part is stretching. And it's expressed essentially as a percentage. So the strain plot should look similar to the stress plot. And you'll see on the strain plot, you can actually see how coarse this mesh was. And you see these brightly colored areas are areas of the highest stress and also the highest strain because they're deflecting the most. So if you were to, for example, remesh this much finer, I'll show you how much longer it might take. Hopefully that works. I'm going to run this now. And when I was running it before, okay, that went pretty fast. So this is a pretty simple simulation. But so now if you zoom in on those areas where before I had two bright red diamonds, now they're somewhere in this green area. And the one other thing, there we go. So there's the strain again. So these ones completely went away. There's still one there. The last thing that I wanted to point out that's that'll tell you how accurately you think you have your simulation set up is before you even run the simulation, and then while you're looking at it, try to imagine what you expect the part would look like if it was loaded in this way. So if I'm holding the base of the part where the screw holes are and pushing on one face, it makes sense that I would expect to see it deflect in that direction. If I was going to go and edit this definition and flip it to be reversed and then rerun it, I would expect that the circular boss on the top should flex in the other way, and it does. So that makes sense. So have in mind what you think you should be seeing before you get to the end. We'll talk about this undoubtedly more. I hope that that was helpful.